Good day, I'm Norman Wildberger. Today we're going to begin looking at irrationality in mathematics. It's a major problem with the subject. Our approach to irrationality doesn't work. Most senior mathematicians are aware of this at some level, but they would rather not address the issue and acknowledge it. Many junior mathematicians and most students are blissfully unaware of the problems. Nevertheless, the problems are serious, they're deep, they affect so many things. They weaken mathematics and they make it much less beautiful than it ought to be. It's a big subject, so we're going to start slowly. Today we're going to look at historically the first example of irrationality, which concerns this idea of the square root of 2. The question, is there a number whose square is 2? As the Pythagoreans realized, this comes up naturally in geometry because the ratio of the side of a square to the diagonal of a square is exactly this kind of thing. So the Pythagoreans actually realized that there was no such number, and it caused them a lot of consternation. But that difficulty has extended and extends even now today, casting a long shadow over many parts of mathematics. One of the challenges in talking about this is that inconveniently there's not just one square root of 2 that's floating out there. There are in fact 3 different square root of 2's, in quotes, which are found today in mathematics. And 2 of them are perfectly fine, make complete sense, can be established without any doubts or ambiguity, while the third simply doesn't work and represents a severe confusion and maybe some dishonesty as well. So there is an applied approach to the square root of 2. There is an algebraic approach to the square root of 2. And there's an analytic approach to the square root of 2. These are all quite separate, even though we're using the same symbols. So it's easy to get a little bit mixed up in these discussions. So one of our jobs is to clearly differentiate between these different approaches in order to point out that this one, which is the most popular one, and the one that most people ascribe to, doesn't work. Okay. So analysis, modern analysis is a very weak subject logically, and the origins of the problem are already contained in this square root of 2. Okay, so the problem historically goes back to the ancient Greeks who appreciated the importance, this conundrum of the square root of 2. And it's also really the first example, I suppose, of an irrational number, which was incorporated into mathematics in the modern sense by Stevin in the 16th century. He introduced the idea that the decimal number system of the Hindus could be extended to capture things like the square root of 2, or pi, or e, or other so-called real numbers. All right, there were very serious problems with this decimal system approach. We're going to talk at length about them, but today we're going to focus on the square root of 2. And a good place to start is to go back to the Pythagoreans. In the early days of Greek mathematics, so around 500, 600 BC, the arithmetic and the geometry were of a relatively primitive kind. They were still not comparable in depth to the Babylonians or the Egyptians, from which they learnt a lot of their mathematics. Nevertheless, they made one very remarkable accomplishment, having exactly to do with this question of the irrationality of the diagonal of a square, or this root 2. So what we're talking about here is the Pythagoreans, followers of Pythagoras, and their understanding that the side and diagonal of a square were incommensurable. And it all comes down to Pythagoras' theorem, which is, of course, the most important theorem in mathematics. Let me remind you how the ancient Greeks thought about this, and you can also go back to the earlier videos in this series to get some more information. So we have a right triangle here. meaning that this side and this side are perpendicular. Then we can create squares on each of the three sides. And supposing that we have a notion of area, we can talk about the area of this square, let's call it Q1, the area of this square, Q2, the area of this square, Q3. And Pythagoras' theorem is that Q1 plus Q2 equals Q3. So if we have a perpendicular sides there, then this relation between the areas holds. Now, a special case of that is the case of an isosceles right triangle, which is something like this, where this side and this side are congruent. And you can think of this as just being half of a square. I haven't drawn the other part of the square, but we really have a square here, and that's really the diagonal of a square. In this case, this area, or I prefer to call it quadrants, this quadrant's Q1 and this quadrant's Q1 are equal, and Pythagoras' theorem is that Q1 plus Q1 equals Q3, or 2 times Q1 equals Q3. So far, there's no problem. It's all well and good. The problem arises when we try to interpret area in terms of distance. In other words, when we take the square root of Q1, when we say that this area is actually this length times this length, because we have a square here. So when we try to convert quadrants, Q1, to distance or length, the problem arises. This area is d1 times d1, or d1 squared. So this relation becomes 2d1 squared equals Q3, which is this d3 times this d3, so d3 squared. And then if you rewrite this as 2 equals d3 over d1 all squared, you see that you've written 2 as a square of this number, which is the ratio of d3 to d1. Now, the ancient Greeks did not think in terms of numbers. They thought of segments as being sort of fundamental objects themselves. This idea that we should associate a length to a segment is a modern idea, not one that the ancient Greeks supported. So they wouldn't have exactly said it this way. But nevertheless, they realized that if you were just simply interested in the relationship between this segment and this segment, that involved some basic incommensurability, because at some point they realized that this kind of thing was impossible. It was impossible if d3 and d1 were commensurable. In other words, if this was a rational ratio, or in other words, a rational number, we would say today. So assuming that the ratio of this length to this length is a rational number leads to a contradiction, because they proved that it was impossible for 2 to be the square of a rational number. Let's have a look at this very important discovery. So here's the theorem that is at the heart of the problem. The theorem is that there is no rational number a over b satisfying a over b squared equals 2. So this result was known to the Pythagoreans, and it was found in earlier editions of Euclid, in book 10, I believe. This theorem is deeply upsetting to the Pythagoreans. Okay, so suppose that a and b are integers. That's what we mean when we have a rational number. And if they're integers, let's suppose that they have no common factor. Because if they do have a common factor, we can divide by that common factor, both of them, to get a new pair of integers which don't have that common factor. So by canceling any common factors, we can get these, the numerator and the denominator, in sort of reduced form. So we're going to assume that we've already done that. That's an important step in the argument. Okay, then we look at this equation and we rewrite it as a squared equals 2 times b squared. These are all integers. In fact, they're natural numbers. This is obviously even because it's 2 times something. And so a has to be even because the square of an odd number is odd. So a must be even. And if you're an even number, then it means you're 2 times some other number. So a is equal to 2 times some other number, c. Okay, now we plug 2c in for a in this expression, and then when we square it we get a 4 here. So the 4 and the 2 cancel partially, leaving us with a 2 on this side now. We get 2c squared equals b squared. And now we can conclude exactly the same way that b must be even, because this is obviously even. B can't be odd because the square of an odd number is an odd number. So b must be even. So we've concluded that a is even and b is even, so they have a common factor of 2. And that's contrary to our assumption. We assumed we had already cancelled any common factors, including 2. So our assumption that this is possible is incorrect. There is no rational number a over b whose square is equal to 2. And for the Pythagoreans, that meant that the diagonal of a square and the side of a square were incommensurable. So it meant that you couldn't go from the side of a square to the diagonal square by equal subdivisions or by equal repetitions. There's a basic incommensurability between these two things because the ratio is not rational. So it's a very important theorem, and it's really the heart and the start of irrationality issues in mathematics. The result that we've just proven is often restated in a very wrong way. So it is very wrong to restate what we've just proven in the following way, to say that the number square root of 2 is irrational. This is often done. You often see this. Okay. No, no, no. What the theorem really says is that there is no number square root of 2. There is no number whose square is 2. This way of writing it suggests that you already have an object square root of 2. And now you're looking at it and saying, oh, we've just shown that this is actually not rational. No. What you have is you don't even have the square root of 2. You don't have such an object yet. That's what the theorem is telling us. There is no square root of 2 to decide, oh, I wonder whether this is rational or not rational. There are only rational numbers, and there is no rational number whose square is 2. So to even write square root of 2 is already at some level some kind of cheat. It's contradicting what we've just demonstrated, namely that you can't write such a thing. Okay, now as I've mentioned, there are currently 3 ways to try to overcome this difficulty. There's an applied approach, an algebraic approach, an analytic approach. The applied approach is to say, let's just work with approximations. Although we cannot find a number, a rational number, whose square is 2, we can find rational numbers whose square is pretty close to 2. And for many purposes, that's good enough. That's an applied approach. There's an algebraic approach, which is to define an extension field of the rational numbers. We're going to enlarge our notion of number to include some new strange object which we've created expressly to have the property that its square is 2. It's a little bit tricky to do that, requires some care, but it's remarkable that that can be done. Then there's the analytic approach, which essentially goes back to Stevin, which is to say, let's use infinite decimals. And probably I should put that in quotes. Let's use infinite decimals or something equivalent to create square root of 2 as a real number. Okay, lots of quotes everywhere here. So this is the modern idea, and it's very highly problematic. Very highly problematic. It doesn't work, to be honest. It doesn't even come close to working. So let's have a look one at a time at these 3 different approaches. The first one, the applied approach, which is the one that's actually used by applied mathematicians, by engineers, and by scientists, even though they may not be completely conscious of having this sort of separate approach to things. The idea here is that the square root of 2, which we might call r here, This thing refers to a rational number which has the property that r squared is approximately 2. So we're looking for a rational number whose square is pretty close to 2, and pretty close is open to interpretation. Pretty close might depend on the particular application we have in mind. In any case, once we've found such an r, we'll say that that r is equal to root 2. So we'll write r equals root 2, even though in fact it doesn't exactly have the property that its square is 2, but it's good enough, it has the property that its square is almost 2. So, for example, 1.4 squared is 1.96. That's pretty close to 2. 1.5 squared is 2.25. That's also pretty close to 2. And this one's a little bit smaller, and this one's a little bit bigger. So we're kind of bracketing 2. A little bit more accurately, suppose we look at 1.41. Well, its square is 1.9881, while 1.42 squared is 2.0164. Both of these numbers, 1.41 or 1.42, are therefore possible approximate values for the square root of 2. This one being a little bit too small, this one being a little bit too big. Well, we can do better. We can look at 1.414 squared, which has this value, 1.415 squared, which has exactly this value, and we're getting closer and closer to 2, even though we're not finding a rational number whose square is exactly 2. 1.4142, there's its square. 1.4143, there's its square. 1.41421, there's its square. 1.41422, there's its square. So for example, if an applied mathematician needed a number that was approximately the square root of 2, they could use 1.4, which would be rather crude. They could use 1.41 or 1.42, or maybe go to 1.414 or 1.41421, even a little bit more accurate. So this thing here could be written as the square root of 2, which is not exactly true, but it's approximately true. So this idea of looking for approximate solutions is both practical and important theoretically. There are many situations where some number or some object or some construction cannot be defined or obtained precisely, but an approximation can be obtained. It's just like the real world. I mean, there's many situations where some ideal is not obtainable, but we can go some ways towards the ideal, and that's of value. Let's have a look at an application that's in line with what we've been talking about. This is sort of in the spirit of this particular video, which discusses this kind of distinction between pure and applied, between accuracy and approximation at greater length. So have a look at that one, Universal Hyperbolic Geometry 20. Let's have a look in this example here at the Fermat curve, which is another interesting cubic with the equation x cubed plus y cubed equals 1. Here's a graph, sort of asymptotic, that line there. It goes through the point 1, 0 and the point 0, 1. And Fermat, in fact, proved that the only rational points on this curve are 1, 0, 0, 1. Which is to say that the only points on the curve are 1, 0, 0, 1. So you might well ask, well, what exactly are we plotting here? If these are the only 2 points, why don't we just have 2 points as the plot? Well, the reason is because we're plotting this thing approximately. And that's a very useful thing to be able to do. In other words, what we are plotting is we're plotting points x and y in the plane for which x cubed plus y cubed minus 1 is close to 0. Not necessarily 0, but say close to 0. And close to 0 might mean different things. It might mean between minus 0.1 and 0.1. Or it might mean between minus 0.00001 and plus 0.00001. It depends. But once we allow some range of values near 0 instead of just exactly 0, then there are lots of points that we can find, and we can plot some number of them and play join the dots to get a graph. And that's in fact what your computer does. Your computer does not look for numbers for which this is exactly true. It only looks for decimal numbers for which this is approximately true. So this is what your computer is doing. It's a useful thing to be able to do. Thinking approximately rather than exactly has many applications, and in some sense it's actually the heart, the key idea of analysis. It's where analysis starts. The idea that we're going to work with things approximately, but we're going to keep control over how much error we've introduced. This idea also influences what we mean by solving an equation. For example, suppose we want to solve the equation x squared equals k, where k is some fixed number. In fact, the problem has 3 cases, not 2 as you might think. The 3 cases are that, first of all, a solution might exist. For example, if you have x squared equals 25 over 9, then a solution does exist. X equals 5 over 3 is a solution. And in fact, x equals minus 5 over 3 is also a solution. Or say here, if you look at x squared equals 4, what we're looking for is we're looking for a value of x down here for which the value of the graph is at this level, at y equals 4. So we're looking where the graph of x squared meets this horizontal line when y equals 4. Well, there's exact solutions, 2 and minus 2. Case number 2 is where there's no solution, but approximate solutions do exist. For example, x squared equals 2. In that case, x is approximately, say, plus or minus 1.414. There are no rational numbers that solve this thing exactly, but there are numbers that solve it pretty close. Which is to say that if we draw a horizontal line through 2, it in fact does not actually meet this graph. But there are points on the graph which come pretty close to meeting it. So same thing here for k equals 3, for example. These points don't officially exist, but they approximately exist. There's lots of points in here that are approximately having the value that x squared equals 3. And the third case, no solution exists, not even an approximate one. For example, x squared equals minus 3, or x squared equals minus 1, pictured here. There's no value of x for which the value x squared is even close to minus 1. I think it's quite useful to think about, given an equation, there are these 3 possibilities. An exact solution, an approximate solution, or no solution. Many times the approximate solution is what we're ending up graphing on the page. Now let me introduce to you this algebraic approach to the square root of 2, which is a very interesting idea and is a very important idea in mathematics. It will be very useful to us. So the idea is to start from the rational numbers and to enlarge the rational numbers to create a slightly bigger arena for doing arithmetic, in which there is an object which is playing the role of a square root of 2 algebraically. So here's how this is done. And this is just a preview of it. We're going to talk at length about this construction and similar constructions later on. Alright, so the new and bigger field that we might be considering here, we might call it rat square root of 2. And the objects are pairs of rational numbers. So we're going to consider pairs A and B. A and B are rational numbers. And we're going to use round brackets. The operations are the following. Addition and subtraction are just component-wise. So they're just like they would be if we're thinking of these as vectors. And it's useful to think of them as just vectors. So there's vectors with the ordinary addition and subtraction, and here's the crucial new operation. We're going to define a multiplication of these two vectors. So a1, b1 times a2, b2 is, by definition, here's how we're going to define it, a1 times a2 plus 2 times b1, b2. That's the first component. And the second component is a1, b2 plus a2, b1. Okay, it looks like we've just pulled this out of the hat, but in fact there is some very good reason for exactly this choice. And I'm going to leave you with some exercises. You can play around with the arithmetic here. Okay, so you can convince yourself that this particular object, 1, 0, plays sort of the role of the number 1. If you take 1, 0 times any vector, you get the vector. You can check, for example, that this multiplication is commutative. If you interchange the order, you get the same thing. And here, a little bit more subtle thing, you can check that if you take some vector a, b, and you multiply it by this particular vector, you get 1, 0. And this vector has components a over a squared minus 2b squared and minus b over a squared minus 2b squared. Okay, do we have to worry about this thing being 0? Well, how could this be 0? If this is 0, it would mean that a squared over b squared equals 2. In other words, that ab all squared was 2. And we know that that's not possible. So it's not to worry. There's never a possibility that the denominator here is 0. So this inverse, we're really finding the inverse of this vector because the product is equal to the 1 in the field. And then you can check that 0, 1 squared, this other unit element, has the property that its square is 2. And that justifies calling it, introducing a new symbol, by calling this thing root 2. And then we can go back to what we started with and rewrite it by saying, all right, we can now rewrite this and sort of informally introduce this notation a plus b root 2. All right, and then more laborious exercise, you can, but fun, is to check that the usual laws of arithmetic hold for these operations. So distributive law, associative law, etc. So this is a new arena of arithmetic which is expressly created in order that it has an object which plays the role of a root 2. But it's important to note that this root 2 that's appearing here has nothing whatsoever to do with that 1.414, etc. that we were talking about previously. Completely unrelated to that decimal. This root 2 is floating freely away from the rational numbers. It's all on its own. Nevertheless, it's a very powerful and important construction. We're going to have to talk more about this algebraic approach to extension fields. So most of you watching this series will probably not think about square root of 2 as an approximation, and you will probably not think about it in terms of some algebraic construction. In your mind, you will think that square root of 2 is some infinite decimal, which starts out 1.414 and goes on in some fashion. That's the third approach. That's the analytic approach, and that's wrong thinking. So I really want to get you to consider the possibility that that is an incorrect thought, that you are sorely mistaken in thinking that such an object exists. It does not exist, my friends. Okay. And mathematics becomes a lot stronger when we look carefully at that situation and that claim and examine it logically, dispassionately. I know there's thousands of mathematicians out there who routinely write down root 2 and imagine it as an infinite decimal every day, but they're all wrong. They are seriously wrong. So, okay, let's try to slowly take a big breath and consider this possibility that we might have to change our point of view. Let's have a look at this analytic approach to root 2, which pretends that somewhere on the line, which up till now only consists of rational numbers, somewhere there's a new place. And it's somewhere between 1 and 2. And there's a new number called root 2. And it has the property that its square is 2. And we can find out what this thing is by making a calculation. In fact, we can go back exactly to the algorithm of finding a square root that goes back to the Hindus that we discussed in Math Foundations 49. In that video, I showed you how to find the square root of a number, an integer, which we already knew was a square. But it's not too hard to see that the same algorithm also works for decimal numbers. And what it turns out is something that we haven't seen before, a new kind of object. So let's have a look at that algorithm. We want to find the square root of 2. So we're going to write 2 as 2.00, and here are all the subsequent zeros in the decimal expansion. Of course, they're unnecessary, but we'll put them there, and we'll separate them in pairs with commas. So what does the algorithm say? The algorithm says, well, first of all, we should find a number whose square fits inside 2, so say 1. So 1 squared is 1. And if we take the difference between 2 and 1, we get 1. And then we pull down a pair of these two zeros and we get 1.00. The point here is not too important. You can think of this as being 100 if you like and ignore the decimal. It doesn't make much difference. Now what we do is we take what we've just got here, that 1, and we multiply it by 2 and put it there. And we write a little blank. And we then look for the next number, which is going to also fit into that blank and has the property that when we take this times this combination, we get something that's close to what we've got there, but just a little bit less. So if we think of this as 100, then if we put a 4 here, then we get 4 times 24 is 96, which is just a little bit less than 100. 3 would also work, but 3 is not the maximum. 5 would be too much because 5 times 25 would be more than 100. So 4 is the right one, and we'll multiply it by 24 to get 96, and then we'll take the difference for just the 4. Bring down another 2 zeros. Now we take the 1.4 multiplied by 2. Okay, 28. I haven't put a little decimal point here. I could put a decimal point in here, but I won't. So 28. And then we need to find this number here, so that if we copy it over here and multiply this times this, we get something that's just under 400. So 1 will work. 1 times 281 is 281. 2 would be too much because we would get something like 560. So that's a 1. Get 281, take the difference, 119, pull down 2 more zeros. Multiply this by 2, 282. Leave a blank. Figure out what number we have to put in here. 4 times this turns out to be this, which is just a little bit under 11900. There's the difference. Take what we've got so far, multiply it by 2, leave a blank. Find a number here such that when we put it here, then this times this is just a little bit less than this. We do that and keep going. There's nothing to prevent us from carrying on. And we can do so. Well, we can do so until our patience runs out, or we fall over, or something stops us. But in theory, we could keep going further and further and further in this algorithm, completely straightforward. So this is an algorithm that just keeps on going and going. It gets harder and harder as we go, because at each step we have to take what we've already obtained and multiply it by 2, and then add another digit. So the numbers involved are getting bigger and bigger and bigger, and there's nothing we can do about that. So after we've gone 1 trillion places here, then we're taking this number with 1 trillion places and multiplying it by 2 to get the next step. So necessarily the program will slow down and slow down. It will get slower and slower because it has to deal with these larger and larger numbers. At any point we can stop and say we've got a good approximation to a number whose square is 2. But at no point do we actually finish this process. It just keeps on going and keeps on going and keeps on going. And there's no appreciably faster way. Okay? There's no much fancier way of computing a square root than essentially doing this. And people have done this to several million places, found square root of 2, but it's a bit of hard work. So what do we end up getting from this? Well, we get something like this. We get a statement that the square root of 2 equals 1.4141213562373095048 80168872420969807856 9671875376948073176 79737990732478462107 038850387534327644157 and so on. And that's the kind of statement that modern analysis makes. And modern analysis claims that we have now found square root of 2, and there it is. Well, usually they don't list as many as I just have. There's usually 5 or 10 listed. But of course, as I've mentioned, it's possible to list many more because millions of these digits are known. So, is this a correct and meaningful statement? Does it make sense to say that the square root of 2 equals this? No, it does not make sense. This is not a correct and meaningful statement. Why not? Well, because the 3 dots at the end incorporate all kinds of additional stuff that has not been done. We have not finished the job. We have not found a square root of 2. In fact, all what we've done by proceeding up to this point is found a reasonably decent approximation to the square root of 2. We have not found the square root of 2. And no matter how much effort and time and energy you put in, you will still be in a similar position. It is impossible for us to finish the task. It is impossible for us to finish and say, ha, now I have the square root of 2. Of course, we do this all the time. We pretend that we have the square root of 2. It's a dishonesty. In God's garden, should there be such a thing, which might be far outside our universe, it may very well be that there's a beautiful infinite stone on which all the digits of square root of 2 appear, where this thing is written out in its entirety, which goes on forever. God possibly has the potential of understanding this thing in its entirety. But here, we human beings in this universe do not have this potential. We are not at the level of God. It is wrong for us to have such an arrogant approach to say, we can do the same thing that God can. We can understand this number. We cannot understand this number. It's wrong even to say, I can imagine this number. You cannot imagine this number. You cannot imagine something that goes on truly forever. Despite what you or anyone may claim, you can imagine something going on for a very, very long time. But you can only imagine that you can imagine the entire sequence. You can't actually imagine the entire sequence. So there is serious dishonesty here in this statement. This is not a mathematically correct statement. If you were marking this statement, you would have to mark it 0 out of 1. It's just not true. Of course, many of you will be so used to making this statement, so used to the idea that analysis understands the square root of 2, you will be loath to admit any weakness in this direction. But consider for a minute. Suppose that we buy for a second that this really is the square root of 2. Suppose we accept these little 3 dots here as somehow adequately representing these untold infinities that go on. What would happen if we reduced the size here a little bit and chopped a few of these digits off? Suppose I remove that 7 and had the 3 dots emanating from there. Would that still be all right? Probably you will say yes. All right, suppose I eliminate that entire row, that row, that row, that row, and say all of this row up to the 2. So is it still true that root 2 is 1.4142 dot dot dot? Perhaps you say yes, because perhaps you've even written something like that. Okay, let me reduce a few more. Let me chop off a few more. How about root 2 is 1 point dot dot dot? Now you're probably starting to think, well, I'm not sure if I would go for that. Let me go one more. How about I just eliminate the 1 altogether and I just write root 2 equals dot dot dot? What essential difference is there? Root 2 equals dot dot dot. A lot of students would be very happy with an arithmetic that looked like that. Got a mathematics question? What's the answer? Just put dot dot dot. Mathematics becomes very easy, doesn't it? So I claim that there's no need to be pretending here. Most analysts are afraid of the consequences of having to admit that this doesn't work, because they think that their subject is going to collapse. It's not going to collapse. What's going to be required is that we look at it again with fresh eyes and fix it. But collapse is not really in the cards. But some work is required. There's an uphill challenge here to fix analysis and to replace waffly notions like this with actually concrete, explicit, true statements. And a good place to start is to go back to that approximation point of view, the applied point of view, and think a little bit more clearly about what's going on there and how we can use ideas of approximation to start thinking about measurement and analysis. Next time, we're going to do just that. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.